Hello everyone. Welcome to our lecture on analog electronic technology. After previously studying the common source amplifier circuit and the small signal model analysis method, in this lesson we will continue with the common drain and common gate amplifier circuits of field effect transistors. We know that bipolar junction transistors have three different configurations, or connection schemes. And field effect transistors likewise have three types. Common source configuration, corresponding to the common emitter configuration. Common drain configuration, corresponding to the common collector configuration. The common gate configuration, corresponding to the common base configuration. Let us now study the characteristics of the common drain amplifier circuit through static and dynamic analysis. First, let us examine this amplifier circuit. The input signal V sub S is applied to the gate, and the output signal V sub O is taken from the source, making the drain the common electrode. This circuit topology is called the common drain amplifier, because V sub O is output from the source. It is also referred to as the source follower. We begin with the static analysis. By shorting the voltage signal source V sub I, we obtain the DC path. Assuming this enhancement mode NMOS transistor operates in the saturation region, we use the characteristic equations and circuit laws, given the known MOSFET parameters and circuit component values, to solve for the gate-to-source voltage and the drain current. In the output loop, the drain-to-source voltage V sub ds equals the supply voltage minus the product of the drain current and the source resistor R sub s. Finally, we must verify that the operating conditions satisfy the saturation region criteria. For the dynamic analysis, we ground the DC voltage source to establish the AC path, then replace the MOSFET symbol with its small signal model to derive the small signal equivalent circuit of the common drain amplifier. Since the drain is at AC ground, we reflect the controlled current source and R sub ds to the lower side. Note that the direction of the controlled source is from the drain toward the source. By moving R sub s to the outer port and performing minor rearrangements, we arrive at the final small signal equivalent circuit shown in the figure. Based on the DC operating point, we calculate the small signal parameters G sub m and R sub ds. From the equivalent circuit, we observe that the input voltage V sub I equals the sum of the gate-to-source voltage V sub gs and the output voltage V sub O. Meanwhile, the output voltage V sub O equals the product of the controlled source current and the parallel combination of R sub ds and R sub s. From this relationship, we derive the voltage gain. Unlike the common source amplifier, the gain expression contains no negative sign, indicating a non-inverting relationship between input and output voltages. It is evident that the voltage gain is always less than unity. When the product of the transconductance and the parallel resistance is much greater than 1, the gain approaches unity, and the output voltage closely matches the input voltage. Therefore, the common drain amplifier circuit is also referred to as a voltage follower. And since the output is taken from the source terminal, it is also known as a source follower. Observing the input port, the input resistance is the parallel combination of R sub G and R sub G2. Note that this input resistance does not include the internal resistance of the signal source. Under this condition, the voltage gain from the signal source equals the port voltage gain multiplied by the voltage division ratio of the input network. To determine the output resistance, we set the independent source V sub s to 0 while retaining its internal resistance. With no load connected, we apply a test voltage V sub t at the output port and analyze the ratio of V sub t to the resulting current I sub t. From the circuit, we derive an expression for I sub t. Since the gate draws no current, its voltage is 0. Making the gate-to-source voltage equal to the negative of the test voltage. From this relationship, we calculate the output resistance, which is the parallel combination of three resistances and therefore typically low. Next, we analyze another amplifier circuit. Because the input signal is applied to the source and the output signal is taken from the drain, this circuit is a common gate amplifier. By opening the coupling capacitors C sub B, C sub B2, and the bypass capacitor C sub G, we obtain the DC path. Assuming the MOSFET operates in the saturation region and given the MOSFET parameters and other circuit component values, we determine the DC operating point. The DC drain current equals the constant current source value. Using the saturation region characteristic equation, we calculate the gate-to-source DC voltage, determine the source potential, and finally compute the drain-to-source DC voltage. We then verify that the operating conditions satisfy the saturation region criteria. For the dynamic analysis, we short the capacitors, ground the DC voltage source, open circuit the DC current source, and replace the MOSFET with its small signal model to draw the small signal equivalent circuit. Neglecting channel length modulation lambda equals 0. From the DC operating point, we calculate the small signal parameters. Using the small signal equivalent circuit, we derive expressions for the input and output voltages and thus obtain the voltage gain, which again shows a non-inverting relationship between input and output. When the signal source is a current source and the circuit parameters meet certain conditions, the current gain is approximately unity, meaning the output current closely matches the input current, i.e., the common gate circuit acts as a current follower. According to the definition of input resistance, we find R sub I equals 1 over G sub M. At this point, we can also calculate the voltage gain from the signal source. By following the same method used to determine the output resistance of a common source amplifier with a source resistor, we derive the output resistance of the common gate circuit. In most cases, it is approximately equal to the drain resistor R sub D. From the above, we see that using the small signal model analysis method facilitates the analysis of various field effect transistor amplifier circuits. Moreover, by examining the common source, common drain, and common gate configurations, we discover that each offers distinct dynamic characteristics, providing valuable ideas and options for everyone when designing amplifier circuits in future coursework. That concludes the key points of this lesson. Thank you.